안- 안녕하세요. This is Verifiable Credentials, past, present, and future. I'm very pleased to be able to present this to you today. I thank the organizers of this conference for inviting me, and I hope that you find this material interesting and useful. My name is Brent Zundel. I am the chair of the Verifiable Credentials Working Group at the W3C. Our group recently standardized the Verifiable Credentials Data Model version 2.0 and a large collection of related standards. I am the Vice President of Standards and Ecosystem at Trade Verified, which is a supply chain compliance and risk mitigation company. At Trade Verified, I lead our efforts to help modernize global trade systems using global, interoperable, open standards. Trade Verified also supports additional standards efforts at the IETF and W3C, such as selective disclosure COSE web tokens, glue identifiers, and decentralized identifiers. I also serve as a member of the W3C Advisory Board. I'm thrilled to be here today. Verifiable credentials were standardized by the Verifiable Credentials Working Group at the W3C. This work was first incubated in the Credentials Community Group starting in 2015. The work was then adopted by the working group in 2017. It took us 2 years, but then we published the first version of the Verifiable Credentials Data Model. Then we produced updates and revisions over the following years. Finally, 10 years after development began, verifiable credentials are a really mature technology that are beginning to see wide adoption. Verifiable credentials enable this three-party model of information sharing. So on one side, we have an issuer that creates verifiable credentials. These credentials consist of some metadata, such as the issuance date, credential status information, also information about the issuer itself, a set of claims that are information about a data subject, and then proofs that tie all of that information together and tie it back to the issuer. The issuer then shares those credentials to a holder. The holder receives the credentials from as many issuers as they need to, and they can store those credentials in a credential wallet that is controlled by the holder. The holder then presents those credentials to any number of verifiers. The verifiers check the proofs on the presentation. They can see that those credentials are tied back to the holder. The proofs in the credentials tie back to the issuer. So you have this unbroken chain of assurance that data hasn't been tampered with, and these proofs are what make the credentials into verifiable credentials. These verifiable presentations are a really essential component, whereas a credential consists of multiple claims from a single issuer. A presentation consists of multiple credentials, potentially from multiple issuers. A presentation also can have a selectively disclosed portions of credentials. Selective disclosure is a very important component of verifiable credential capabilities. Verifiable presentations also make the sharing of a credential a deliberate act by the holder to a specific verifier. It's a consent mechanism. This verifiable credentials data model is built on the concept that modern data can be linked together in semantic graphs. The claims in a credential form a graph of related data. So you have multiple credentials all linked together in a larger graph. Every node in the graph is represented with an identifier. And these identifiers allow any node to reference any other node in the whole graph, and for the semantic meaning of all of this data to be shared deliberately. This graph model is serialized as JSON LD, which is a fully compatible subset of JSON. JSON is everywhere nowadays. Because a verifiable credential is a graph-based model of linked data that is serialized as JSON, we get benefits on both sides. On one side, we have JSON LD. It benefits from using standard JSON tooling. It can be read and understood with common libraries that are easily found and available. On the other side, it's really easy to combine graphs that are shared in each credential with the graphs of other credentials, and to link these graphs with the data in other initiatives. Some examples are these data spaces like GaiaX, or the Digital Product Passport initiatives from GS1 and UNCFAC. Also, you have these Industry 4 initiatives like Web of Things that can make use of these graphs of data. Anywhere that organizations have constructed ontologies of vocabularies and processes can immediately make use of those ontologies within credentials. It ties together these credentials into the existing systems that companies use. This construct of JSON LD also means that verifiable credentials are fully compatible with selective disclosure capabilities and zero-knowledge proof systems. This is what enables the private sharing of personal data. Verifiable credentials are designed for people. They're designed for people to control and use their own data. Instead of a user giving permission for a data provider to communicate about them directly with a relying party, an issuer just signs claims and passes them to the holder as a tamper-evident set of information. The holder can then choose when and how to share this information with a verifier without the issuer needing to be involved. This consent is very important. This means information in a credential can be shared without an issuer knowing that it's been shared. But still, because verifiable credentials are digitally signed, the verifier can trust that the issuer was the source of the information and rely on that information according to their trust in the issuer's reputation. Verifiable credentials are designed for machines. They're machine readable. They can be created and shared with standard JSON tools. Due to the ability to link data, users can have confidence translating the claims into the well-established ontologies they already have in place. Data can be pulled in alongside the semantic meaning of that data. Verifiable credentials metadata includes signed contexts linked to vocabularies that give computers an automatically ingestible means of receiving this data. Additionally, the digital signatures and the status on the credential can be automatically verified. Verifiable credentials are defined in a collection of specifications. Alongside the verifiable credentials data model, we have JSON schema, which provides a way for the syntax and structure of the verifiable credential to be checked. We have controlled identifiers, which define a way to link identifiers such as URLs and their associated keys. This allows controllers of web domains to tie public key information to the control of those domains. The public key information is what a verifier uses to verify credentials that are issued by the controller of the domain. Another example of a controlled identifier is a decentralized identifier, or DID. DIDs work very well with VCs. Bitstring status list enables an issuer to modify the status of an issued verifiable credential. After issuance, the status of a credential may need to be updated. Common statuses that we see are valid, suspended, and revoked, but any status may be used. The verifier checks the status of the credential to make sure it's still valid or to make sure it's not revoked or suspended. A credential without a means to validate it and verify it isn't a verifiable credential. And so the working group also defined two different methodologies for securing verifiable credentials. On this side, we have data integrity, which is a suite of specifications. It enables the semantic meaning to be persisted across transformations of the data. The data integrity suite builds on well-established standards for digital signatures, EDDSA, ECDSA, and the BBS signatures. Alternatively, we have the Jose and Cose specification. This describes how to sign and use verifiable credentials as JSON Web Tokens, as selective disclosure JSON Web Tokens, or as Cose Web Tokens. And since verifiable credentials are JSON objects, a credential can then be signed using any Jose or Cose signing algorithms that are defined at the IETF. So verifiable credentials are designed to be compatible with these other efforts. They're compatible with any protocol that it can exchange JSON payloads, like the OID4VC protocol that's being developed at the OIDF. They're compatible with any Jose or Cose signature algorithms. They're compatible with any tools that can be used to sign, create, and transmit JSON objects. So other advances that we're seeing now, there's a digital credentials API that's being developed at W3C. This API enables user agents to mediate the presentation and issuance of verifiable credentials on the web. So this API will allow browsers and websites to communicate with digital wallets that store credentials and facilitate the sharing of credentials online. Due to their kind of inherent qualities of data protection and provenance, plus their compatibility with JSON tooling, verifiable credentials have become a core component of emerging digital identity infrastructure systems. Two examples of these are the European Digital Identity Wallet, and there's Singapore's Trust VC framework, among others. These digital identity systems using verifiable credentials provide holders with the ability to share information about themselves using this privacy-preserving technology. Verifiable credentials are also a very key element in global trade modernization efforts. Verifiable credentials can be used to represent bills of lading, purchase orders, commercial invoices, bills of materials. These credentials can then be shared between the entities involved in global trade, up to and including the regulators who require this information in order for goods to be imported. Without verifiable credentials, these systems have to make do with scanned documents or PDFs, with information that's often presented in person or by hand. Collecting and presenting this information is a difficult, time-consuming, and costly task that verifiable credentials can simplify and make much more efficient. These modern trade systems, built on verifiable credentials, anchor trust in every transaction, while enabling the protection of sensitive information using selective disclosure. So using verifiable credentials, combined with proper identification of the involved entities using glue identifiers and proper linking to public keys using controller identifiers, modern trade systems are poised to save literally billions of dollars through these new efficiencies. The selective disclosure allows for companies to share only the minimal set of information that's required while safeguarding intellectual property and confidential corporate information. These tools allow for the required advanced traceability of key assets and components to coexist alongside the need for preserving proprietary data. Verifiable credentials are adaptable to any set of information, far beyond identity systems or global trade. They can be shared independent of any centralized authorities or control, and without any loss of semantic meaning. Once a system speaks VC, there's this minimal need to retool or refactor in order to be compatible with new credential types. A system designed to verify credentials for government identification information can also be used to verify credentials containing digital product information. Issuers and verifiers that issue and ingest verifiable credentials no longer need to specially designed APIs for meaningful data exchange with each other. These issuers and verifiers don't need to be involved in deliberately setting up communication paths with one another and working out APIs and access controls. The holder has become the communication path. The holder is the API. The holder removes the bottleneck between the issuer and the verifier, and it removes the need for the issuer to be involved in the presentation of the data they've signed. As we move into the future, because verifiable credentials are compatible with JOSE and COSE, they also automatically benefit from the development of post-quantum signature algorithms. Once these algorithms are standardized as part of JOSE and COSE, verifiable credentials can seamlessly use those new algorithms. So as the world continues to modernize and make digital equivalents of analog processes, verifiable credentials serve as a vital building block to make sure that privacy and personal control of information is safeguarded. These systems are already being put into place. For example, if you received a digital vaccination credential during the COVID-19 pandemic, then you've already used verifiable credentials, and this allowed you to easily share personal information in a privacy-preserving manner. The future is very bright with verifiable credentials. Grateful for the opportunity to share this information with you. I hope you all have a very wonderful conference, and I was glad to be able to be a part of it. 감사합니다.